Have you ever wondered what actually separates a junior developer from a truly senior backend engineer? Look, it's not about memorizing syntax or knowing the trendiest framework. It's about surviving the harsh, unforgiving reality of production failures. Welcome to This Explainer. Today, we're bridging that massive gap between theoretical system design and the messy reality of systems that actually scale. We're going to look at the exact architectural patterns that keep giants like Stripe, Uber, and Amazon running flawlessly under immense pressure. We're covering scalability trade-offs, those common engineering mistakes everyone makes, and practical back-end advice you can literally apply to your systems today. Let's get into it. Okay, we need to start with a hard, inescapable truth. TCP guarantees delivery, sure, but absolutely does not guarantee exactly one's semantics. In a distributed system, network failures aren't just a possibility, they are completely inevitable. Relying on basic network protocols to prevent duplicate requests, that is a recipe for disaster. Think about it. A request might succeed on the server, but the acknowledgement gets lost on its way back. So the client assumes a failure and just retries. If your architecture doesn't actively account for this physical reality, I hate to say it, but your system is already broken. And this right here is the massive mindset shift you have to make. Junior developers tend to build for the happy path, right? Perfect networks, single requests, everything working seamlessly in a local environment. But senior engineers, we build for production reality. They know that network timeouts happen constantly. They anticipate dual write failures, like where a database saves perfectly, but the message queue just randomly crashes. They expect duplicate messages. Designing for this chaotic reality is what makes an architecture genuinely resilient. All right, part 1, the distributed system nightmare. Let's look at a visceral production failure that happens thousands of times a day at scale if you aren't careful. Imagine this scenario on a platform like Uber. Step 1, a user clicks Pay Now at the end of their ride. Step 2, their mobile network hiccups and the request times out. Step 3, the user panics and clicks Pay Now again. And step 4, well, without specific architectural guardrails, that simple little network timeout leads directly to double charging the user. In the real world, this isn't just a bug, it means customer support nightmares, hefty chargeback fees, and serious regulatory scrutiny. Moving on to part 2, consistency with the outbox pattern. So, how do we actually prevent this cascading failure and keep our databases and message queues perfectly in sync? We use our first senior architectural pattern, the transactional outbox. Notice the stark contrast between these two approaches. A fragile system attempts to save an order to the database and then immediately tries to send an event over the network to another service. If the network drops in between those two actions, boom, your system is corrupt. A robust system, however, saves the order and an outbox message in one single atomic database transaction. Instead of writing all this complex retry code to handle network failures after saving data, we just delete that risk entirely. It becomes a guaranteed all-or-nothing operation. Let's break down that atomic transaction. In step 1, we save the order. In step 2, we save the event payload to a dedicated outbox table living right there in the exact same database. Step 3, we commit. Because it's a single database transaction, it is literally impossible to end up in an inconsistent state. Then, a completely separate background process will come along later, read that outbox table, and reliably publish those messages over the network to your queue or event bus. It's brilliant. Part 3, idempotency, making retries safe. Because our outbox processor guarantees at least once delivery, we now have a totally new problem to solve: handling duplicate messages safely. This brings us to a foundational concept. In mathematics, f of x equals f of x. Sounds like a college math class, right? But in plain engineering English, an operation is idempotent if executing it multiple times yields the exact same result as executing it just once. This acts as a really strict contract between the client and the server to make retries completely safe. The client promises to use the exact same unique key for retries, and the server promises to intercept any duplicates and just return the original successful response without reprocessing all the logic. This is exactly how Stripe prevents millions in duplicate charges every single year. When a client makes a request, they generate a unique UUID, an idempotency key. The server first checks an incredibly fast distributed cache like Redis to see if that key already exists. If it doesn't, it inserts the key with a processing status, charges the card, and then updates the cache with the final result. If the client retries because of a timeout, Stripe just sees the key in Redis and simply returns the cached result. That card is absolutely never charged a second time. Uber extends this concept to incredible lengths. They actually use an idempotency key tied to a specific trip ID for their entire ride completion workflow. So if the app crashes right in the middle of updating the status, or charging the rider, paying the driver, or sending the receipt, it's actually not a problem. Retrying the workflow with the exact same key resumes the process perfectly without any data corruption. It's a lifesaver. All right, part 4, ultra-low latency event pipelines. Now that our events are safe and consistent, we need to process them at massive scale. Processing at that scale requires a massive shift in how we think about data structures. As engineers at the LMAX Trading Exchange discovered, traditional queue data structures and locks are dramatically slow. They act as massive bottlenecks in concurrent processing. If you're aiming for true high-performance backend architectures, standard queues actually introduce latency costs that are in the same order of magnitude as writing to a physical disk, which is wild to think about. So let's break down how senior engineers bypass this limitation. The LMAX disruptor pattern relies on fixed-size circular ring buffers. You're basically trading a tiny bit of upfront memory footprint for absolute deterministic predictability. It uses sequence gating to coordinate producers and consumers without those heavy, slow database locks. And crucially, it uses cache line padding to avoid false sharing across CPU threads. The cost of a little wasted memory through padding is far cheaper than the massive latency spikes caused by CPU cache contention. So what is the actual real-world impact of these optimizations? By serving data directly from optimized memory using these lock-free single-writer architectures, you can literally make your processing 10 to 100 times faster. You drop your latency from sluggish milliseconds all the way down to the microsecond level. This isn't just some minor tweak. It fundamentally alters the throughput capabilities of your entire platform. It's a real game changer. Which brings us to part 5, strategic code deletion. We've added these advanced patterns, but there is one final paradigm shift that separates the novice from the true master. It's not about what you add, it's about what you take away. Senior developers don't write better code, they delete more of it. Your value as an engineer is actually inversely proportional to the amount of code you write. Think about it. Every single line is a liability. Every line is a maintenance tax, a potential bug waiting to happen, and a piece of cognitive load that the very next developer has to try and understand. This creates a really stark contrast in your career trajectory. A junior developer joins a team and proudly adds 50,000 lines of new features and elaborate edge case handling. A senior developer joins and systematically deletes 15,000 lines. They remove entire unused microservices and consolidate redundant logic. The fascinating reality is this: the developer who gets promoted is the one who eliminates complexity, not the one who creates it. So, here are your tactical steps for strategic deletion. First up, delete redundant code. Go combine those similar functions. Second, ruthlessly remove unused features. If you have an analytics dashboard nobody looks at, kill it. Third, eliminate premature optimizations. If you have some complex caching layer for data that changes maybe once a month, or elaborate failover systems for low-traffic internal services, just delete them. I promise you, do this and watch your bug reports drop and your team's velocity absolutely skyrocket. So I want to leave you with this final provocative thought. What fragile code can you delete from your architecture today? It is time to stop writing happy path code. Start implementing robust guardrails like the transactional outbox and strict idempotency keys. Protect your systems, optimize for true mechanical sympathy, and ruthlessly eliminate complexity. Thanks for joining me on this explainer. Now go open up your codebase and find something to delete.